Good morning, dear students. Thank you all very much for coming. My name is Pavel Kantor, and I'm from Technical University of Ostrava, NET Center. Topic of my today's talk is sludge treatment in Czech Republic and co-incineration of sludge. I'm going to divide this presentation into five main parts. First will be introduction, then we'll tell you some characteristic of sewage sludge, sludge composition, factors that establish the sludge, wastewater treatment, formation and division of sludge, and amount of sludge. Then sewage sludge treatment, and then something about utilization of sewage sludge and utilization in practice. Let's move on sewage sludge. Nowadays, the issue of sewage sludge disposal is becoming a serious problem. Due to the membership of the Czech Republic in the European Union, this area is becoming more and more frequently discussed, and thus calls for a solution as quickly as possible. Looking at the speed of human society's development, it's clear that sludge production will continue to increase, and sludge management methods used to date will not be enough. However, we must not forget that the development of other methods is largely influenced by economic and legislative factors. Our accession to the European Union has tightened the conditions for the use of sludge in agriculture and storage of sludge. The essential requirements for the Czech Republic stem from the implemented European Union Directive 91/71/EEC. The directive is also fundamentally opposed to the disposal of sludge in landfills. This creates space for the search for new alternative options for the use of sewage sludge. An example could be our experience from abroad, where the energy use of sludge is proving possible. Another is the European Union Council Directive, which was adopted for the use of sewage sludge in agriculture, which determines the conditions for their use, application, registration, and control. All this in a comprehensible form for producers and processors, in this case farmers, who apply them to the soil. Based on this, municipalities with more than 2,000 equivalent inhabitants should have a mechanical, biological, two-stage wastewater treatment plant. This requirement was to be met by 2005. Taking a closer look at the number of wastewater treatment plants built, we find the number of wastewater treatment plants built under the European Union Directive by the end of 2005 is approximately 180. The directive also strongly opposes sludge disposal in landfills. Due to the different types of wastewater treatment plants, it's necessary to individually solve the most suitable method of sludge management. The task is to comply with the requirements for the protection of the environment and to health of persons handling sludge at minimal cost. Sludges that have the required chemical composition can be used as a substitute for industrial and livestock fertilizers. Then we accept them as an alternative source of minerals and organic substances. In this way, we can compensate for the soil deficit of these substances in the soil. Sludge is a term that can be described in several ways. One of the definitions tells us that sludge is a mixture that consists of two or more waste substances. At least one substance from the mixture should be of liquid state and thus form a so-called continuous liquid phase. This solid phase contains at least one further substance and it's dispersed again in a continuous liquid phase. Another definition is that it's a heterogeneous mixture of organic and inorganic substances. Sludge is a very valuable source of organic matter. Sludge contain a large amount of essential nutrients and trace elements, and also sludge has the ability to improve physical, chemical, and biological soil conditions. Uh, Raw sludge has a water content of approximately 93% to 99%. Therefore, dewatering or drying can be necessary for further utilization. The second main component is a dry substance, which is made up of organic and inorganic substances. Uh, Organic substances, we can divide them into two groups, into non-toxic and toxic substances. Non-toxics, they are represented by up to 60%, and we include mainly sugars, fats, proteins, waxes, and also nitrogen and phosphorus compounds. Sludge also contains potassium, but to a lesser extent than nitrogen and phosphorus. Toxic substances includes hydrocarbons, pesticides, polyphenols, and heavy metals. Not only organic substances are here, but also inorganic substances. These inorganic substances includes quartz, feldspar, carbonates, or iron oxides. Uh, important are also microorganisms. Microorganisms are represented to a large extent. Most microorganisms are pathogenic, as human and animal excrements are usually found in wastewater. That's why we find viruses in them that can cause serious diseases, as well as bacteria and parasites. We talk about wet matter. Now, the dry matter is obtained after evaporation of all the water at 105 degrees of Celsius. It consists of organic and inorganic substances. Mineral composition of sludge. We can determine it by X-ray diffraction method. The main fractions of sludge are quartz, calcite, vivenite, which arises as a result of technology used in wastewater treatment. In smaller quantities, we find a diverse mixture of minerals, which includes Elite, muscovite, kaolinite, and some types of feldspar. Other minerals include diomite and magnetite. Most of the minerals found in the sludge got here due to flushing from roads or soil due to rainfall. After grain size analysis, it can be stated with a high probability that the sludge contains mainly materials that are fine grained. It means that they are less than 0.045 millimeters. These fine grained particles can present in the dry matter up to 95%. Furthermore, there are particles whose size is larger than 0.5 millimeters. It's a very diverse mixture of minerals and various organic residues, both of plant and animal origin, like seeds, hair, etc. As was mentioned before, sludge can contain also heavy metals. Increased concentration of toxic substances is mainly caused by elements for which the set limit values are monitored and evaluated. These values must be observed in cases where the sludge will continue to be used for applications on agricultural land. In situations such as this, it is therefore necessary to make a thorough analysis of the soil and set limits on toxic elements which are dealt within degree of the Ministry of Environment. Monitoring and analysis are carried out mainly at those treatment plants for which the intention is to use the resulting sludge on agricultural land. The number of currently monitored wastewater treatment plants is around 100 facilities. Toxicity is monitored for elements such as arsenium, cadmium, lead, copper, and mercury, and also others. The form in which the risk elements occur in the sludge is usually insoluble due to the pH range of the sludge. The bioavailability of heavy metals in soils and sludge is not dominated by their total concentration, but by soil properties. The bioavailability and mobility of metals therefore rests mainly on the physicochemical properties of the sludge-soil mixture. Increased soil toxicity may occur when sludge containing more than one heavy metal is applied. Accumulation of heavy metals is found mainly in the upper layers of the soil. Plant contamination is thus most risky in soils with low absorption capacity and pH less than 6. The most available metal that accumulates in the upper layers of the soil is zinc. Sludge contains also a large amount of aerobic and anaerobic microorganisms, which contribute to the decomposition of organic matter contained in the dry matter, which reaches up to 70%. Most of these organisms are useful and necessary during sludge treatment. I would now like to focus on organisms that are pathogenic and can cause a number of diseases, not only in humans and animals, but are also dangerous for plants and the environment if the sludge is applied to the soil and not properly monitored and treated. Negative impact has been observed, for example, in potatoes, in which cysts have formed, which cause some species of nematodes. The danger of pathogenic organisms lies primarily in the production of toxins that are toxic and can permanently damage animal tissue. Therefore, it's essential to subject the sludge to chemical and thermal treatments in order to eliminate most pathogenic organisms, including the spores or eggs. Especially for certain species of parasites, we divide pathogenic organisms occurring in sludge into four basic systematic groups. The first are bacteria, then viruses, then protozoa, and worms. Selection sludge examination details the main analytical protocols for the following properties. Dry matter content at 105 degrees Celsius, then suspended soils 105 degrees Celsius, then fire loses, there are more options, 105 degrees to 180 degrees, then 105 to 250 degrees, then 105 to 550 degrees, and the final 555 to 900 degrees. Another properties are weighted elementary composition, especially for organic sludge, then temperature, pH, oxidation reduction potential, conductivity, alkalinity, fats, fiber content, pathogenic agents, salinity, chlorides, amounts of water bound in with suspended solids, and quality of sludge interstitial water. Sludge structure can be identified by the following factors. Apparent viscosity in relation to rheological behavior. Slimy suspensions are non-Newtonian liquids. The figure found will depend on the type of rheometer used and on the strain shear energy applied. Therefore, when stating a sludge viscosity, the type of rheometer used and strain applied must also be specified. Another factor is penetrometer test. This test provides a comparison index used to estimate the more or less paste-like structure of dewatered cake. Slump test. This is an important factor for sludge storage design. Sludge is regarded as solid when piled up to 1 meter height. It forms an angle of at least 30 degrees with the ground. The last factor is granulometry. It's for thermally dried sludges. Then factors that are used to identify the behavior of sludge undergoing dewatering are thickening capability. Let's see drainability tests and sludge thickening. Then characterization of filtrability, compressibility, limit dry solids content, and centrifugability. For this, see sludge examination, centrifugation, and filter press. We recognize 5 types of formation and division of sludge. The first is primary sludge. Primary sludge is separated from the polluted water during sedimentation of the particles. This happens in settling tanks. Due to the high content of undissolved substances, the structure of this sludge is mostly granular. The nature of the sludge depends on the composition of the wastewater. After removing all the water, the dry matter content is around 50%. In addition, there are putrefaction processes, thanks to which the sludge smells unpleasant. Another one is secondary sludge. It separates in the settling tank, where the biological stage of purification takes place. The structure of the sludge is flaky, which negatively affects its dehydration, which is more difficult than in the primary sludge. The color of the sludge ranges from light gray to dark brown. Composition also depends not only on the nature of the wastewater, as with primary sludge, but also on the technologies used during treatment. Impurities that haven't been completely removed during the treatment of the primary sludge, like gravel fibers, may still be present in the secondary sludge. It's more often called active sludge. Then we have raw sludge. It occurs when the primary and secondary sludges are mixed together. Chemical sludge, its formation occurs in wastewater treatment plants in which chemical precipitation of phosphorus is performed. In the Czech Republic, ferric sulfate is the most widely used for phosphorus precipitation. Sludge from biological filtration consists of dead cells of microorganisms and inner substances that are trapped on the filters during biological filtration. The advantage of the filtration is low sludge. Production of the sludge in Europe is constantly growing due to expansion of the sewage network, which flows into various wastewater treatment plants. The growth is expected to increase several times in the most of European countries in coming years. Exact amount of sludge is converted to the liters of sludge generated per person per day, or to the generated weight of sludge dry matter in grams per person per day. Production of sludge from municipal wastewater treatment is between 150 to 170,000 tons in recent years. During determining of total amount of sludge, the primary sludge is the highest part of amount because the primary sludge contains a lot of minerals and organic substances which can be degraded during the sludge treatment. Sedimentation or activation tanks can be used as temporary stores of the sludge. For evaluating of sludge treatment systems, it's necessary to estimate amount of generating sludge. Part of the primary sludge can be easily determined by a successful elimination of solids. The highest efficiency system is if the elimination of solids is around 50 to 70%. Sludge treatment systems can be divided into three groups based on concentration of sludge. The groups are, we can divide them on problematic system, sludge with concentration of 3%, then average system, sludge with concentration of 4.5%, and optimal system, sludge with the highest concentration, about 6%. The estimate of amount of chemical sludge depends on stoichiometry and amount of chemicals. Amount of biological sludge, it's more difficult to estimate. Number of methods and procedures must be followed. Video jsem tam nahrál, takže by to třeba mohlo být na 1,5 hodiny. Aby to tam, jo? Jo, no jako uvidíte, když ne, tak to prostě vymažu. Vidíš tady. Factors influencing biological sludge production. Value of BODN.
Ale musí za to dobu vlastně amount of the organic matters to bude něco od body.
In the picture, you can see sewage sludge disposal from urban wastewater treatment by treatment method. These data are from 2070s. Typically, 4 different types of disposal make up a considerable share of the total volume of sewage sludge treated. At least half of the total was used as a fertilizer for agricultural use in 2 European Union member states, Ireland and Lithuania, as well as in Norway. By contrast, 84% of sewage sludge was composted in Estonia and 53% in Luxembourg. Alternative forms of sewage disposal may be used to reduce or eliminate the spread of pollutants on agricultural or gardening land. These include incineration and landfill. As there are more and more environmental concerns about the latter, incineration is increasingly the method of choice. While the Netherlands, 98%, Germany 64%, Belgium 79%, and Austria 53% reported incineration as their principal form of treatment for disposal. Discharge into control landfills was practiced as the principal type of treatment in Malta, Serbia, and Bosnia and Herzegovina. In these countries, it's the sole form of treatment. And also Romania and Croatia. Sludge is generated in a wastewater treatment plant into which polluted water flows through sewers from human settlements. The polluted water contains a lot of organic and inorganic substances which began to accumulate in the settling tank. Depending on the amount of water, the sludge can have different concentrations. After the particles settle, putrefaction process takes place as the bacteria present here begin to decompose organic matter. We distinguish that generated sludge according to the place of collection from the system. How this wastewater treatment plan works, we can show you on the video.
It's a topic we'd rather not think about. Where does last night's dinner go when we flush it down the drain? While you may already be grossed out just thinking about it, this question leads way to a significant subset of civil engineering and a massive amount of public funding. Just like all dogs go to heaven, all drains in a city lead to a wastewater treatment plant where that wastewater gets turned back into water that we can drink. Now, you may be thinking that you'd rather just let bygones be bygones and not think about this nasty part of real life. But here's the thing. Chances are you've drunk water that was waste at some point, so you might want to take some time to understand this engineering process that makes dirty water clean. Here's where it starts. The toilet. Once you're done doing your business and flush that magical handle, your waste ends up at the inlet of one pretty interesting place, a wastewater treatment plant. Why is this place so interesting? Because it takes arguably one of the most disgusting substances in the world and turns it back into something that is essential to all life. Flushing just your toilet at halftime may not seem like a big deal, but when you couple it with thousands, if not millions, of others doing the same, it can result in some pretty high sewage flow rates. New York City has an array of 14 wastewater treatment plants that handle a combined 1.3 billion gallons of wastewater daily. That's enough wastewater to fill the Dead Sea with pure sewage in just 8 years. And that's just New York City. There are an estimated 14,748 treatment plants in the US alone that 76% of the USA's population relies on, according to the American Society of Civil Engineers. Understanding wastewater is crucial to understanding the critical infrastructure needed to support modern life. That brings us to the first step of the process that handles larger items in sewage, things like flushable wipes, 2x4s, toys, or even guns. You name it, and it's probably been caught in a bar screen. Bar screens are exactly what you would think. They are large vertical bars that stand at the inlet of nearly every wastewater treatment plant, designed to stop larger items from getting to the plant and hurting machinery like pumps. This first process where bar screens are used is commonly referred to as pre-treatment. The sole intention of pre-treatment is to remove the outliers in the sewage and make the whole mixture a little more homogeneous, or slightly less chunky. Bar screens are typically mechanically raked at certain intervals, depending upon the flow rates of the the water treatment plant, although some older plants will still have more manual removal processes. Whatever is removed from the bar screens is then sent off to your average landfill or solid waste handling facility. Or, in the case of unusual items such as guns, they're sent off to the evidence locker in a police station to be investigated. Next up is the grit chamber. Grit chambers are the next steps in the pretreatment process following bar screens. Since these bars don't catch everything, larger particles called grit still need to be removed from the sewage as it is made even more homogeneous. As the sewage flows into the grit chamber, the velocity of the rather viscous sewage is adjusted to allow for particles of sand and rock to settle out. This is needed because these particles can't be removed using chemicals, and they could potentially clog or destroy pumps later on in the process. There are 3 types of these chambers: horizontal grit chambers, aerated grit chambers, and vortex grit chambers, which all accomplish the same task using slightly different methods. Following the grit chambers, the sewage will move on to the primary treatment process, which starts with a large basin called a primary clarifier. Primary clarifiers and clarifiers in general function on the principle of settling velocity. This term can be defined simply as the speed at which a particle settles. For wastewater being pumped into clarifiers, it's important that the flow rate of the water being pumped in doesn't exceed the settling velocity of the particles trying to be removed. In order to accomplish this, engineers will vary the size and number of primary clarifiers in accordance with the plant's permitted sewage flow rate. This ensures that at varying flow levels, solids can settle out of primary clarifiers to the correct quantities. At this step in the process, the slightly treated wastewater, which is referred to as effluent, is free of solids larger than 10 micrometers and should be all organic matter, which will be treated further. The top layer of the clarified water flows over a weir wall and into the next basin in the process, called the aeration basin. Now begins the process of secondary treatment, the sole focus of which is to significantly degrade the biological content of the sewage. In many cases, this process starts with aeration basins. Effluent flows into the aeration basins, at the bottom of which are hundreds, if not thousands, of tiny air blowers that create bubbles through the water. The water is pumped into this tank along with something called return-activated sludge. You can think of return-activated sludge as a bunch of happy little bacteria that get to eat their favorite foods all day long. This introduction of significant amounts of bacteria along with the massive amounts of oxygen injected from the bubblers creates an environment perfect for the process of aerobic digestion. Summarized simply, it's the breakdown of organic matter along with the use of excess oxygen. Some older plants will add in another step before aeration basins referred to as biofilters or trickling filters. Found in many older plants, these filters essentially trickle the effluent over a medium like stone or plastic and allow for a film of bacteria to chow down on any organic matter in the water. This step is largely not used in newer plants due to more efficient and effective modern processes, but for plants with basins already installed, many still use them because they only benefit the treatment process in most cases. Following aeration basins, the effluent along with much of the sludge is pumped into a secondary filter or clarifier, where some of the sludge is removed and pumped back into the aeration basins as the return-activated sludge. Further settling of larger particles is also accomplished in these basins, as it is the final step of the process that will remove solids and larger biological matter. Water flows out of secondary clarifiers over a nearly identical weir wall to the primary clarifiers and moves on to the disinfection process. At this point, 85% of all organic matter is removed from the water, and the effluent should be safe to drink in most cases, although you probably wouldn't want to. Disinfection is the final step of the process and is usually accomplished in one of 3 ways, either through chlorine, ozone, or ultraviolet disinfection. Each process has its benefits and drawbacks, with each being used commonly throughout the wastewater treatment process across the world. Chlorine disinfects the water through chemical disinfection. Chlorine, which you can think of as concentrated bleach, is added to the effluent here to kill off any remaining bacteria and organisms still living in the water. When chlorine is added to kill off the bacteria, it then has to be removed before it can be discharged, as to not kill off anything in the discharge location. After this, the water is safe enough to discharge into a stream or lake. Ozone disinfection is another method of disinfection that involves pumping an electrical current through the water that causes oxygen molecules, O2, to disassociate and combine with a free oxygen molecule, forming O3, known as ozone. Ozone is an incredibly strong oxidant and causes microbes' cell walls to leak, rapid cell decomposition, and overall damage to cells. In other words, it kills off bacteria. The last common method uses ultraviolet light to scramble bacteria's DNA so that they cannot multiply. In UV disinfection, the bacteria in the water aren't killed, rather they're sterilized, rendering them harmless. If you were to ingest water with living microbes immediately following UV treatment, any harmful bacteria would be unable to multiply or render your body damage. Engineers choose between these methods based on a variety of factors such as flow rates, cost, and location of discharge, which brings us to the final step, effluent release. Effluent release exists in one of two forms. In most cases, the now treated water is released back into a stream or lake or other water source. In rare cases, usually in areas where water is scarce, the effluent discharge from a wastewater treatment plant can be discharged into another treatment plant directly where it will be treated further for consumption. This is referred to as full-cycle water reuse. From a chemical perspective, the final drinking water is the same as normal treated water that flows through your pipes now, but due to the connotation of your drinking water being sewage just days before, this treatment process is normally shied away from or not heavily publicized. The entire process of wastewater treatment takes on average 24 to 36 hours from when a drop of water enters to when it leaves. Each wastewater plant will receive a permit for flow rates, chemical levels, and effluent quality, among other things, from the EPA that outlines the necessary treatment for a plant. Wastewater plant operators will make adjustments to a plant's operation and constantly measure levels to ensure proper discharge and proper treatment. Without these operators and the dirty job that they do around the clock, our sewage would always stay sewage and sanitation in modern cities would be much, much worse. Wastewater treatment is an essential dirty job, and you can thank the 14,748 treatment plants in the US alone for not having to worry about what happens when you flush.
What is the wastewater? Wastewater is water from households, municipalities, and cities, atmospheric water in which physical or chemical changes have affected its quality. Wastewaters are drained through sewer network. The first one is sewage wastewater. They contain a high amount of organic substances, and up to 80% is facial contamination. Therefore, sewage wastewater is full of bacteria. The highest numbers are in the warm summer. With decreasing temperature, their amount is significantly lower. From the inorganic substances, fluorides, phosphorus, and nitrogen are the most represented. The undissolved substances in sewage are approximately 200 to 400 milligrams per liter, where about 73% are settleable and 27% non-settleable. The pH value is in the range of 6.5 to 8.5, which means that the water is neutral to slightly alkaline. Then there is industrial and agricultural wastewater. If there is a quantity over the maximum values and the sewers are overloaded, industrial and agricultural buildings can be ordered to discharge wastewater at a constant flow rate. The composition of industrial wastewater is diverse due to the diversity of industries. Therefore, the pollution is mainly of organic and inorganic origin. Organic pollution is mainly caused by the food, paper, textile, and pharmaceutical residuals. Industries engage in the mining and processing of ores, the production of fertilizers, ceramics, and glass result in pollution by inorganic substances. Due to the different composition and concentration of pollutants, it's necessary to use specific technologies. This wastewater can be treated separately or together with sewage. They can only be discharged into sewers if they meet the permissible limits set by the sewer regulations. This must be kept by each operator, together with a list of substances that must not be discharged into the sewer. The last one are atmospheric waters, the areas where water can be captured, parking lots, roof, etc., also play an important role. After contact with the surface, we divide them into unpolluted and dirty water. Before contaminating, Ministry of Agriculture coordinates the implementation of controls over compliance with obligations related to the use treated sludge on agricultural land. The Central Institute for the Supervising and Testing in Agriculture checks the compliance with the obligations when using treating sludge on agricultural land. It imposes penalties for the breach of the obligations pursuant to the Act number 156 slash 1/1998. Fertilizers, soil conditioners, auxiliary plant preparations, and substrates, and on agrochemical testing of agricultural soils, the Fertilizers Act. Support technologies for the recovery of sludge from municipal wastewater treatment plants are used for monitoring and evaluating the quantity of the sludge from municipal wastewater treatment plants and the quantity of sludge utilized for application to the soil. On the basis of legislatively established microbiological and chemical parameters, vigorously check the quality of treated sludge for application to soil. Also, these support technologies supports from public funds investments associated with energy recovery of sludge from municipal wastewater treatment plants with adequate sludge production. Also, they promote research focused on the monitoring of residues of pharmaceuticals and personal care products in wastewater and their penetration into sludge from municipal wastewater. Based on the research, results continuously design and implement measures to dispose of sludge from municipal wastewater treatment plants with regard to the protection of human health and the environment. Also, in cooperation with the Ministry of Health, promote the awareness campaigns focused primarily on the citizens to provide guidance for the disposal of pharmaceuticals, chemicals, and waste in accordance with the legislation in this area. And also, these supporting technologies reflect legislative changes in the European Union in the area of waste sludge from wastewater treatment plants, with the emphasis on protecting human health, the environment, and in particular the soil in applying sludge from municipal wastewater in agriculture. In this part of the presentation, we'll focus on the technologies that can achieve the required quality of treated water. Therefore, the assembly of a complete technological treatment line and sewer network are very important. Different types of sludge are produced in different parts of treatment steps. Sludge management controls sludge treatment. Sewage sludge is usually treated by one or several of the main following treatment steps. These steps are stabilization, sanitization, dewatering, and thickening. The first one, sludge stabilization. The sludges are stabilized in order to reduce organic matter, other producing, and to eliminate pathogenic organisms. Stabilization of sludge can be done by chemically or biologically methods. Uh, it can be aerobic stabilization, anaerobic stabilization, or chemical stabilization. Aerobic stabilization. During aerobic stabilization, biodegradable substances are oxidized. The purpose is to prolong the age of the sludge beyond 20 to 30 days or to aerate the excess activated sludge in the stabilization tank. The content of organic substances in dry matter is in the range 40 to 60, and the amount of living microorganisms is below 10%. Also, methanization tanks have mostly avoid shape with conical neck. Inside this tank, there are mixing unit and thermal insulation unit. Heating is performed with hot water, steam, or heaters. Producing biogas is collected in floating gas bell, and stabilized sludge is pumped out several times per year. Chemical stabilization. This stabilization is based on a reaction with calcium oxide, which reacts with water to form calcium hydroxide and heat. Quicklime is supplied in an exact amount to reach pH higher than 12 for at least 2 hours. After 14 days of treatment, the value of pH must be more than 11. Most microorganisms become inactive after increasing pH value and thus cannot participate decomposition of sludge. Advantage and disadvantage of this method. This method is simple and has an excellent hygienic effect, but the disadvantage is that dry matter of sludge increases and also release of ammonia into the air. In sludge after sanitization, the numbers of pathogenic microorganisms have been minimalized to the exact required value. For sludge, sanitization is used process with lime or heat. What about sludge thickening? The primary purpose of sludge thickening is to concentrate these solids, reducing the volume of sludge. It reduces operating costs, hydraulic load of sludge management, and simplifies its final processing and storage. Sludge thickening is provided by gravity and mechanical processes to remove water from the sludge. After thickening, optimal content of dry matter is around 6%. The most commonly used thickening processes include gravity thickening, flotation centrifuges, and sludge dewatering belt. Sludge dewatering. The purpose of dewatering is to reduce the volume of sludge to prepare it for its effective disposal and incineration. Sludge dewatering process uses centrifuges and belt press dewatering or dewatering in sludge fields and lagoons. In contrast to sludge fields, sludge lagoons have natural bottom without drainage. Disadvantage of these two methods are space consuming and climate changes. There are two types of dehydration: direct and indirect drying of sludge. During indirect drying process, the heat is transferred to dried material by thermal surfaces. Sludge don't come into the direct contact with stem or hot oil. The final products are granulate or briquettes. In direct drying, heat is supplied directly to the material by hot gas. The most commonly used dryers is rotary drum dryer, fluidized bed dryers, and belt dryers.
It's a
In the European Union, wastewater treatment plants produce up to 30 kg of dry sludge per capita per year. The estimated annual sludge production in Europe in 2020 is 13 million metric tons of dry matter. The approach of individual countries in the European Union to sludge management is very different. In 2017, Germany burned 64.5% of the sludge produced, as we can see in figure 1, and Austria 53.5%. In other countries, the share of incineration is significantly lower. Hungary 27%, France and Poland 17%. The use of sludge in agriculture within the European Union is currently regulated mainly by the Council Directive, where limits on heavy metals are listed. However, it's outdated and doesn't express the current needs of requirements for the safe application of sludge in agriculture. The pros and cons of each approach to sludge recovery are listed in Table 1. Sludge used in agriculture can easily create a diffuse source of environmental contamination. However, some European Union countries have reduced the use of sludge on agricultural land to avoid the risk associated with contaminated emergence concerns and pathogens. Large wastewater treatment plants in Germany will not be allowed to use sludge as a fertilizer or as a component in a compost. A key factor in the revised regulation is the introduction of a future obligation to recover phosphorus in all treatment plants that have a total phosphorus content of more than 20 grams per kilogram in the sludge dry matter. There is currently a 12 to 15 year transition period. From January 1st, 2032, there will be a ban on the application of sludge on agricultural land for waste water treatment plants with 50,000 to 100,000 population equivalent, and for wastewater treatment plants higher than 100,000 population equivalent. In the future, it's expected that the need to obtain phosphorus will also be introduced for treatment plants with a smaller population, less than 50,000 population equivalent. Wastewater is also used for irrigation and fertilization. Irrigating short rotation coppice plantations with wastewater solves farmers' water shortage problems and can also reduce fertilization costs for them. Research in this area is underway. For example, in Greece, where the possibility of fertilizing sludge and wastewater with hemp hibiscus, which is grown to obtain fibers, was investigated. The cultivated plants showed the same properties as the plants grown with conventional fertilizers. During the use of wastewater for irrigation, the responsibility lies with both the farmer and the wastewater treatment plant. The farmer is authorized to inspect and take soil samples. The wastewater treatment plant maintains contact with the competent authorities and can thus be responsible for data collection. Specifically, treated wastewater must be used for such a purpose which will no longer composting. This is more complicated method of use, which requires high demands on the quality of sludge. Composted sludge must be of excellent quality, especially in physical, chemical, and microbiological parameters. The sludge to be composted must also contain sufficient organic matter and nutrients. Water content also plays an important role. Sludge, which contains a high amount of water, doesn't create suitable conditions for the multiplication and growth of microorganisms. In this case, the sludge can only be composted if it's used in a suitable mixture with other organic waste, which is degradable and with low water content. In order for biodegradation to be successful, the compostable mixture should optimally contain 70% of organic matter with a water content of 55%. Too high humidity causes a drop in temperature and reduces the oxygen content of the material. Otherwise, slows down the process. And when it falls below about 15%, the microorganisms stop working completely. Uh, the proper functioning of microorganisms is also further affected by pH and the carbon to nitrogen ratio. The problem is that the sludge can contain high amounts of heavy metals and pathogenic microorganisms, which affect the further use of compost. Material is just composted at a temperature that eliminates pathogens. The composting products is then applied to the soil with regard to the quality. When sludge has the established criteria, stabilization, it can be used for recultivation. Depending on the sewage sludge treatment technology and consistency of treated sewage sludge. It's effective method how to utilize sludge from big wastewater treatment plants and to produce biologically active reclamation material, a mixture of waste soil, fly ash from the combustion of fossil fuels, and also from stabilized sludge from wastewater treatment plants. Method is suitable for the reclamation of landfills, waste pumps, and also excavated mining areas that will not be used for agricultural production. Monthly consumption of toilet paper in Netherlands is 1 kilogram per month. The length of the fiber in the toilet paper is standard parameter in the range of 1 to 1.2 millimeter. The size of the fibers affects their occurrence in wastewater in the grain size class below 0.35 millimeters. This information was used to implement the cellulation process, which can be used instead of or in conjunction with the primary treatment of sewage treatment plant. Up to 40% of total suspended solids are captured when the wastewater passes through the bar screen. Industrial filtration is followed by purification and sterilization at very high temperatures. The resulting product is high-quality resale cellulose fibers, which are widely used in various industries, construction paper and board production, or are used for the production of polymer granules. Phosphorus is one of the biogenic elements. It's crucial for energy metabolism in the form of adenosine triphosphate. It carries macroergic energy transferic bonds and is a key component of DNA and RNA. In an organic form, phosphorus is part of phospholipids, phosphoproteins, and nucleic acids. The daily nutritional consumption of humans for phosphorus is in the range of 1.8 to 2 grams. Because phosphorus is obtained from non-renewable resources, it's on the European list of critical raw materials. Critical raw materials form a priority area of European Union's Circular Economy Action Plan, which aims to promote their efficient use and recycling. Sludge contains 2.2 to 4% of phosphorus, from which struvite can be produced, with an estimated sales market price ranging from 188 to 763 euros per ton. 485 to 811 euros per ton compared to the sales price per ton of phosphate rock amounting to 220 to 332 euros. Phosphorus is removed from wastewater by biological accumulation in biomass or by chemical precipitation. Approximately 10% of the total amount in the inflow thus flows from the wastewater treatment plant. The rest is bound by the activating sludge. Removal of phosphorus from wastewater stream with struvite technology takes place at 80 wastewater treatment plants in Japan, USA, and Europe with an efficiency of 40 to 50%. Phosphorus recovery from sewage sludges or sewage sludge ash is much more efficient, reaching up 90%. The high costs, including energy consumption, associating with obtaining phosphorus from ash after sludge incineration, are an incentive to find alternative methods for obtaining phosphorus by direct leaching. The highest phosphorus leaching efficiency, up to 82%, was achieved using sulfuric acid. Ion exchange was used to remove iron and manganese. The yield of precipitation of magnesium ammonium phosphate, struvite mineral, by the addition of ammonium and magnesium hydroxide at molar ratio phosphorus to nitrogen to magnesium is 1 to 3 to 4, reach 57%. The following technologies are used in operation: Rimnat, Airprex, Prisa, Pearl, Pirog, Rifos, and Nuresis. Haber grid washer can be used to separate map crystals from the sludge suspension with a fluidized bed system with a pressure measuring system that affects the density and size of the map crystals. Thermal processes using sewage sludge disposal can be divided on monoprocessing and CO co-processing. Monoprocessing can be monoincineration using fluid combustion reactor producing heat and electricity plus sewage sludge ash. Then there is a gasification, thermochemical conversion, which is producing syngas production and ash. Then there is a pyrolysis with thermochemical conversion producing syngas plus biochar. That was for monoprocessing, and now CO co-processing. This we can divide it on power plant, where is fluid combustion reactor and heat and electricity plus ash is produced. Then cement factory with cement rotary kiln producing cement. And finally, incineration of municipal solid waste, which is in cement rotary kiln with grate boilers, fluid combustion reactors, or rotary furnaces, and it's producing ash. CO firing is usually the case of fuel replacement, power plant or cement factory. In the case of municipal waste incinerator, the sewage sludge addition can be maximum of 20%. Power plants, incinerators, cement plants can be used to obtain energy, heat, where sewage sludge can be used and co-fired. In Germany, from 2029, co-firing for sewage sludge from wastewater treatment plant is higher than 100,000 population equivalent will only be possible if the phosphorus content will be less than 20 grams per kilogram. Mono incineration with phosphorus recovery or sewage sludge ash disposal will be possible if phosphorus content will be higher than 20 grams per kilogram. Sewage sludge is considered as a renewable energy source. It contributes to reducing greenhouse gas emissions. Combustion of sewage sludge is not considered environmentally friendly. Dewatered sludge contains up to 75% water, which is used to remove energy. The calorific value of dry anaerobically stabilized sewage sludge is 9 to 12 megajoules per kilogram, while for food waste it reaches up to 18.5 megajoules per kilogram. The technology of co-firing coal with sewage sludge is used mainly in Germany, Poland, and is being tested in the Czech Republic. Originally, only 5 to 10% addition of biomass or 5% was used for large-scale coal biomass co-firing power generation because at a higher amount of 10 to 20%, slugging and fouling in boilers occurred. Emission limits for stationary emissions sources can be met even with the addition of 20 to 30%. Studies of co-firing coal with sewage sludge show that the addition of biomass affects both the content of heavy metals in fly ash. Chromium, copper, nickel, lead, zinc, and iron, and the amount of fine particulate matter, especially particles below 2.5 ppm in emissions. Today, a relatively high percentage of sludge is disposed of in a thermal manner. Special combustion equipment are used for the process of the sludge can be incinerated in KO incinerators or cement kiln. It's necessary to pre-dry the sludge to remove excess water, and the sludge is not sticky. The end product is ash, in which most heavy metals remain. As sludge is a renewable energy source, combustion is therefore an excellent way to produce electricity, which can be expected in the years to come. There are 170 sludge incinerators in operation in the USA, which use incineration technology, multiple hearts, fluidized bed, and electric infrared. Some sludge is co-fired with municipal solid waste in combustors with suitable technology for refuse combustion. There are currently 27 mono-incineration facilities for sewage sludge in operation in Germany. Mono-incineration facilities burn sewage sludge at operating temperature of 850 to 950 degrees Celsius. At temperatures below 850 degrees Celsius, the occurrence of odorous substances is a problem, and temperatures above 950 degrees Celsius, synthetic can occur. The concentration of phosphorus in sewage sludge ash is around 9%, which correspond to the concentration contained in the mined rock. However, the high concentration of iron and aluminum in sewage sludge is disadvantageous. You can see these concentrations in table 1. It requires a higher consumption of sulfuric acid during its processing. A number of technological problems with the removal of iron and aluminum or heavy metals have already been overcome, which is documented by the high increase in operational equipment for obtaining phosphorus from sewage sludge ash. The resulting products of technology are most often phosphoric acid the calcium phosphate, calcium hydroxyapatite, and phosphate containing ash. Ash phos technology, like Rainbow Denmark, in Rainbow Denmark, was chosen an example of successfully implemented technology, which is currently under construction, with the plant commissioning in 2023 or 2024. After burning the sludge, the ash is dissolved in the ash is dissolved acid without pressure and heating. Phosphorus, iron, and aluminum are separated from the solution by precipitation. The so the solution is neutralized and heavy metals are removed. The resulting product is pure calcium phosphate, ferric chloride, and aluminum hydroxide. Calcium phosphate is used to make NPK fertilizers. It's meaning like nitrogen, phosphorus, and potassium. Ammonium phosphate and ferric chloride and aluminum hydroxide are used to make coagulants used to treat wastewater. 50 to 60% of the ash consists of acid insoluble silicate sand, which can be used as a component to replace cement in the production of the gasification of biomass, raw organic feedstock available in several typologies in nature, represents a process through which it's possible to produce energy with a remarkable reduction of greenhouse gases and atmospheric pollution. This process also allows to reduce the costs related to the management and disposal of certain biomass that is continuously produced, such as sewage sludge, the residual semi-solid material that is produced as a byproduct during sewage treatment of industrial or municipal wastewater. An alternative and innovative approach to traditional land spreading is to use dried sludge as fuel for thermochemical processes such as gasification, which can greatly reduce the volume of the separated waste product inside the main treatment plant. Singa Smart technology is designed to process not only woody biomass but also other organic residues, including sewage sludge. In fact, through a proper pretreatment process, including drying and briquetting, sewage sludge can be introduced into a SingaSmart gasification unit in order to convert the organic compounds into a useful flammable gas. With a variable heating value depending on some feedstock parameters such as inert content, ashes, carbon content, lower heating value, and so on. This approach offers the double benefit of both volume reduction and energy generation. In fact, through suitable gasification process, the whole dried sludge mass can be sterilized and reduced to 5 to 10% of the original volume, leaving as byproduct a small percentage of char that can be further processed to recover elements such as phosphorus or metals or disposed. This approach also allows to concentrate pollutants in a small solid fraction. On top of that, there's the additional advantage of energy availability. In fact, the resulting syngas can be used, for example, in sludge drying, thus creating a circular economy and reduced impact upgrade of the whole wastewater treatment plant. Sewage sludge gasification is an innovative and profitable alternative to business as usual management, particularly in small medium size plants where transportation and disposal represent a relevant cost item. The energy that can be recovered from sludge gasification offers additional financial benefits, especially in those wastewater plants where there is no biogas recovery. On-site sludge processing allows also to reduce the fermentation occurring to biological matter left in an open environment, therefore reducing the release of greenhouse gases such as carbon dioxide and methane. These gases can be better used in syngas. And syngas smart gasification also includes the carbon storage benefit offered by the carbon negative process. The conclusion is that sewage sludge valorization with syngas smart technology offers both financial and environmental benefits and represents a perfect example of biocircular economy application. Another solution is represented by the methods of thermal conversion, which is not yet industrially applied in the European Union. The Pyrex system is being tested as free wastewater treatment plants in Germany. Dried sludge is first gasified at a temperature of 550 to 600 degrees of Celsius and then carbonized by the supply of a controlled amount of air. A resulting product is a product usable as a fertilizer. This product is biochar. The process gas released during the gasification of the input biomass is combusted at the temperature of 1250 degrees Celsius in a flux burner. At these temperatures, there is no condensation of organic compounds and tars. Use of pyrolysis in sludge processing is limited by the high content of heavy metals in biochar. The problem is solved by addition of chlorinating agents during pyrolysis, which significantly reduces the concentration of heavy metals by up to 86% in biochar and bioavailability phosphorus. Municipal wastewater treatment technology is a very good example for the application of circular economy principles in several levels in order to achieve the best possible material recycling, nutrient recovery, and energy utilization by improving conditions for anaerobic digestion, removing cellulose fibers from toilet paper, etc. The Terra Nova Ultra technology, which is based on hydrothermal carbonization, allows for energy efficient sludge drying to a small amount of solid fuel and integrated phosphorus recovery. Thus, treatment and disposal costs are reduced. The hydrothermal carbonization technology of Terra Nova Ultra runs under the exclusion of air at approximately 200 degrees Celsius and under a pressure of more than 20 bars. This process ensures that the toxins in the sewage sludge are destroyed or can be disposed safely. Non-organic toxic waste, such as heavy metals, are bound to the sewage sludge coal and safely disposed through incineration in suitable systems. Organic toxic compounds, such as pharmaceutical residues, are largely chemically destroyed and lose their toxicity. The sewage sludge coal is sterilized by the high temperature and the pathogens are completely killed off. The synthesis of dioxins or furans is impossible with the Terra Nova Ultra process. In addition, toxic waste has long been an unused source of nutrients such as nitrogen and phosphorus, which are both valuable fertilizers. For the first time, a large portion of these nutrients can be recovered economically through the Terra Nova Ultra method, either as a topsoil forming organic fertilizer or as a basic material for the fertilizer industry. In view of decreasing natural resources, the growing demand and rising prices, phosphate reutilization is of particular importance. Within Terra Nova Air, ultra phosphorus is leached out from the sewage sludge and recovered by absorption of natural minerals. The resulting product is a granulate phosphate fertilizer that already today complies with upcoming legal regulations. The very moderate amount of chemicals, as well as the easy one-step process, allows for low production cost of recycled phosphorus. I will introduce you this method in this short video. As part of initiative to protect the environment, Suez prefers sludge destruction solutions with limited impacts and that create value. The destruction of sludge from residual waters can produce steam or electricity. The sludge destruction processes deployed by Suez can destroy sludge, evaporates water, burnt organic matter, and limit the impact on the environment. They reduce polluting emissions and olfactory nuisances. Finally, they are energy efficient, produce steam or electricity.
Every day, cities and towns need to treat wastewater and its sludge, which is an energy-intensive process. At Anglian Water's Great Billing Wastewater Centre in the UK, they don't just treat the wastewater sludge. They convert it into valuable products using Suez's Monsell Advanced Anaerobic Digestion and a combined heat and power gas engine. Here's how it works. Anglian Water's Great Billing facility brings in sludge cake from other nearby wastewater plants via truck. After unloading the truck into the raw sludge system, the imported raw, untreated sludge cake is blended with the sludge indigenous to the Great Billing site. The combined sludge is blended prior to being transferred to the digestion plant to provide a consistent material for the advanced digestion process. The biological hydrolysis process is the key enabler of advanced anaerobic digestion. It pre-treats the sludge to allow the existing digesters to treat more sludge and increase the volatile solids conversion rate. The biological hydrolysis process optimizes the sludge temperature. Initial heating brings the sludge temperature to 42 degrees Celsius or 108 degrees Fahrenheit. In the final stages of the process, the temperature is raised to 55 degrees Celsius or 131 degrees Fahrenheit, which neutralizes pathogens and enables the broader system to produce an enhanced biosolids product. From the biological hydrolysis plant, the hydrolyzed sludge is transferred to the digesters. In the absence of oxygen, the digesters' bacteria break down the sludge to create a biogas at an optimal rate. Because of Suez's patented biological hydrolysis process, digester performance is dramatically improved, achieving higher gas retention with shorter digester retention time in comparison to conventional mesophilic digestion. This allows significantly more sludge to be treated in the existing infrastructure. At Great Billing, the amount of sludge treated through existing digesters was increased by 3 times using Suez's process, which allowed the plant to become Anglian Water's main regional sludge treatment center. Methane-rich biogas is drawn from the digesters and converted into renewable electricity and heat using CHP gas engines. At Great Billing, sufficient renewable electricity is generated to meet the demand of the entire wastewater treatment plant, with surplus electricity exported to the national grid. Heat recovered from the CHP unit's cooling systems and exhaust gases provides virtually all the heat needed to support Suez's advanced anaerobic digestion process. Following digestion, the digestate is sent for dewatering to produce cake used for land application as a nutrient-rich fertilizer. Suez's advanced anaerobic digestion technology can be applied to both existing and new-build wastewater treatment plants. Suez's process guarantees digester performance, which allows water utilities to harness the energy that is present in wastewater sludge and transform from energy users to energy producers.
Mitsubishi's newly developed sludge incineration system with zero energy consumption enables power generation that exceeds the inner plant power consumption and is high efficiency power generation. The combination of the heat recovery from high temperature exhaust gas and high efficiency binary generator achieves power generation exceeding the inner plant power consumption. This significantly reduces greenhouse gas emission. Their original MCOM control system results in a reduction of fuel and electricity requirement because of its optimized control of combustion air and fuel quantity. I will show you a video where you can see how this Mitsubishi incineration system works.
We have an extensive track record for designing and building over 30 sludge incinerators. By combining the incinerator with a high-efficient ORC generator, we have created a newly developed sludge incineration system with zero energy consumption using 72% water content undigested sludge, which generates more electricity than inner plant consumption. We received an order for Asia's first commercial sludge incineration plant with no energy consumption using an ORC generator from the Tokyo Metropolitan Government in 2016. We will deliver the plant with a capacity of 250 tons per day in March 2020. Now, we would like to explain about our new sludge incineration system with zero energy consumption. The main feature of this system is a highly efficient heat recovery system, composed of the combination of ORC generator and exhaust heat from the furnace. The first part is a heat recovery system. This uses a thermal catalyst heater, which enables us to minimize the size of the plant and recover heat positively. Heat recovery and the amount of power generation can be maximized by arranging the thermal oil heater and air preheater in parallel. This creates approximately 1,000 kilowatts of power generation, which exceeds the inner plant consumption, and surplus power can be used in other facilities. The next part is ORC generator. For this system, the high-efficiency binary generator from Turboden SRL of Italy, part of the Mitsubishi Heavy Industries Group, is utilized. This product has been used in over 300 projects worldwide in the biomass and geothermal power generation fields. This generator can achieve extreme efficiency of 24%, while a steam turbine generator is limited to around 17%. In addition, it has resistance to load variation, which maintains stable power generation. Finally, let's take a look at optimum incineration by our original MCOM control. With conventional sludge incinerators, air and fuel is overconsumed as furnace temperature is controlled only by fuel and air temperature. Using optimized control of combustion air and fuel amount or controlling air temperature by MCOM results in a reduction of fuel and electricity consumption and dinitrogen monoxide emission. We then further improve the efficiency of the system to suit the sludge characteristics by introducing remote monitoring and AI control. Our new sludge incineration system results in zero energy consumption while optimizing power generation by heat recovery from high-temperature exhaust gas. Sludge incineration system with zero energy consumption.
A number of researches are currently underway that focus on the use of sludge as a substitute for ceramic clay and clay for brick production. Sludges from the wastewater treatment, which are characterized by a high alumina content, are widely used for this purpose. Materials with a sludge content of 5 to 30%, from which bricks are fired at temperatures between 800 to 1000 degrees Celsius, are tested. Products show high mechanical resistance without deformations and defects. They have high density and flexural strength. These new materials can be used to create terracotta products, refractory ceramics, lightweight aggregate, glass ceramic products. Sludges can be replaced by brick clay, mainly because they have a very similar chemical composition. Its use in the construction industry is technologically attractive and highly economical and ecological. The ratio of sludge to clay depends on the specific composition and nature of both materials used. Thank you very much for your attention. And if you have any questions, you can contact me, and I will try with my team to respond